half of lecture on 27th of October on process control, production automation, how we design controllers. The design criteria are related with obtaining specific values, desired specific values for performance indicators, or specifying desired values for some of these performance indicators and putting some boundary for the rest, or using integral criteria as cost function that is minimized, considering limitations in these inequalities. So the parameters of the controller are the tuning parameters which are changed. They should be positive, and differentiating is optimal when we compare with integrating by this relationship where D is between 0 and 0.5. So the cost functions are integral performance indicators in the form of integral squared error, most widely used. In this case, the error is the difference between measured output, this is the oscillatory step response, and the reference, the dashed line. The result is the thin line, but the error can be positive and negative. In both cases, it's not desired. It should be 0. That's why it is to power 2 and results in this big decreasing positive oscillations, and the integral is the area. So we need to find the area for some K, PTI, and TD, and use optimization approaches to change this K, PTI, TD in a direction that will guarantee decrease of ISE cost function. So optimization we want to minimize by changing the tuning parameters, but this results in very high control action. That's why there is a modification of this integral criteria, putting the control action to power 2 with some weighting coefficient A, which is experimentally obtained, so that the ranges for E and U are the same. And the idea is to minimize this complex function because minimizing error causes increase of U. We cannot, we have to make compromise, not very great decrease in E, but at reasonable small control action. Otherwise, the first term will be very small, but the second will be too large, and the total criteria will not reach minimum. There is something very interesting. This time domain integral squared error criterion, because the integral the areas are reducing, the integral has finite value for the time 0 settling time, for the time of the transient response, the step response. So this can be equivalently represented in the frequency domain, where this is the frequency signal of the error, which can be computed knowing the closed loop transfer function. S will be substituted with j omega, but this closed loop transfer function considers output error, input reference output error, which means that we have to find the feed-forward path between reference and error. It is 1. And the loop transfer function, which is C controller and plant product transfer function. So 1 plus C P is the denominator. So I gave this in the previous slide. So this is okay, but the numerator is 1, the feed-forward path between input and output. Here the output is the error. That is how, in this transfer function, we substitute S with j omega to obtain this frequency response. And the signal is transfer function multiplied by input. Input is step function. The step function in Laplace is equal to 1 over S, and S is j omega. So this can be obtained directly from the proper transfer function, and we can solve this in the frequency domain. Usually this cost function is minimized as an additional criteria when we apply some other criteria and combine with this. The idea is that when you have one criteria, you can obtain one of the tuning parameters. The PID controller has 3 tuning parameters, so we usually can optimize as a second criteria this integral criteria, and use a third relationship to obtain, for instance, the third parameter to be function of the obtained TI, taking D in this range. So the important for this Parseval's theorem is that this integral in the frequency domain is solved for the significant frequency ranges for the system. And this frequency band is determined by the zero or near zero frequency. This is the steady state, and the cutting frequency. So all frequencies which have important magnitude in the magnitude frequency characteristic. So you see how settling time is transformed into cutting frequency. Settling time actually is the initial frequency. Here we have inversion. This 0 corresponds to some cutting frequency instead of infinity, while this final settling time, mathematically infinity, is equal to frequency 0. So this is easier to compute in the frequency domain. The integral is substituted by a sum, and you take discrete values of frequency in this significant frequency range. The design problem for the controller, we can fully design a controller using analytical controller design. The control algorithm is non-standard, often difficult to accomplish in engineering practice. So what we do usually use conventional controllers which are linear. So transfer function of the plant is known. It is also a linear model. And the algorithms of this conventional controller is from the algorithms that combine the 3 terms, proportional, integral, plus derivative in different combinations. So first we have to design the structure of the controller. So how many control loops, the interaction between the loops. So there are additional compensators for peak time delay, for disturbance, for interaction in MIMO, multi-input, multi-output plants. So we have to determine all these control loops and compensating open feed-forward structure. Then we have to tune the controllers in this whole control structure. For this purpose, we need the generalized plant transfer function and the linear zone around the operating point. Operating point means input-output. Output should be equal to reference. So we know the output and we can compute the input, which is actually the control action that will reach this particular reference or output. In the neighborhood, we can test if the step responses at different operating point give constant value for the ratio K for the gain of the plant. So this means that the gain is preserved constant. Also the dynamic parameters, time constant, time delay from the model are also almost constant. So we determine the linear range. So the linear range is important because for this linear range, we have obtained graphically approximation to Ziegler-Nichols model of the step response of the plant. And also these parameters of the plant will be used to tune the parameters of the controller. So we select which algorithm. The compensating controllers have specific algorithms. Then beside the plant, the type of algorithm, we have to know which is the design criteria, what specifications would be reached using this design criteria. So we have to know the performance indicators which are necessary to be ensured by this controller. And these performance indicators lead us to selection of the proper design criteria. So we use tuning of first, second, and high order systems in different applying this theory. So imagine you have a first order system. So no delay, because the delay adds infinite degree of the system. So to obtain first order system, the characteristic equation plant controller should be first order. So if we make the necessary common denominator transformation, we'll obtain, this is our characteristic equation, S is to power 2 first order system. So the combination of plant, time lag, and proportional controller results in first order system. We can have first order system if we have gain with PI controller. But usually the plant has inertia, which is, the inertia means the polynomial of S in the numerator should be higher, of higher degree than in numerator, or at least equal. S in numerator corresponds to differentiation of input. So here, this polynomial in numerator is related with operations over the input, in the numerator with the output. So when we have this relationship between the degrees of S in the two polynomials, this is a result of the cause result relationship over a real world element. This means you cannot have output unless a little earlier input is applied. So the reason is input and the sequence. So the reason is the cause, the input is the cause for output to appear, the result to appear. So this inertia requires this relationship between the degrees of the two polynomials. In the numerator for the time lag, we have 0 degree of the polynomial, and the numerator has first degree of the polynomial. The characteristic equation has one root, and this root can be located at prescribed distance from the imaginary axis in the root plane, which is related with the settling time and the stability index. So the real root magnitude, it should be in the left half plane, this root, but the absolute value should be equal to desired stability index. This stability index can be computed on the basis of desired settling time. So, solving this, S that causes this equal 0 is rho. So a rho depends on the gain. The plant is given. So the gain depends on the desired location, stability index of the root, and Kp should be positive. So there is a relationship that should be made positive. What values to take for the desired location? We use the following interesting relationship. Phew, I cannot get rid of this. Okay, can you see now? I doubt. So, if we want for prescribed the step response from some initial value without any change of reference or disturbance, but initial value which is not equilibrium, the step response develops at using this decreasing exponent. And at some time equal to desired settling time, we want this step response to reach a very small value, the initial value to be reduced epsilon times. From this equation, for the desired settling time, we obtain the relationship where desired settling time and the degree of decreasing initial condition to give us the desired location of stability index. So if we want for 100 seconds to decrease the initial value by 10 times, 1/10, this logarithm 1/10, then we can compute CD. Usually it's taken in this range and it's considered the fastest process with minimum settling time for 0.7. So everything in this formula is known. We select value so that the Kp becomes positive despite this minus in the numerator. The step response when we have one real root, is always overdamped. We cannot tune a controller to give some oscillations. It's not possible because it is a first order system with one root which cannot make a complex conjugated pair. Why complex conjugated pair? Because we have real gains in the characteristic polynomial, and this is possible for complex conjugated pair of roots. It's not possible for one root only complex conjugated. Now, second order systems, all possible combinations are given in this table. If you have proportional controller and you have to tune only one parameter, the self-regulating plant can be second order, 2 time lags, or without self-regulation, integrator and time lag in series. They are transfer functions 1 over S multiplied by K over Ts plus 1. Or we can have also PD controller with these transfer functions, or PI controller, PID controller, and integrating controller. They can make a second order system only for plant of first order with self-regulation, or only integrator without self-regulation. So we'll take an example to see. So because we have a second order system, the characteristic equation has two roots. They can be real different for overdamped process, critical if equal real, or underdamped complex conjugated pair. The criteria for overdamped and equal roots, both the first root should be at distance located CD, so we'll have stability index this computed on the basis of the necessary settling time, while the other very far from the imaginary axis, not to influence the step response of the closed loop system. When they are equal, they will be made equal to this stability index. To reach underdamped response, we have to place the roots somewhere in the plane where alpha is equal to CD and alpha over beta is desired degree of oscillation. So we have two requirements and you can compute two parameters. Example. We have a PI controller. This is the controller, Kp in brackets 1 plus 1 over TIS. And time lag, combination PI controller time lag. Common denominator is obtained and the polynomial is of second order. So this is the characteristic equation equal to 0. So remember that the characteristic equation is 1 plus Cs multiplied by Ps. We substitute this the transfer functions by the transfer function of the controller Pi, and time lag the transfer function of the model of the plant. So we have here second order system. The roots, according to the formula, depend on the discriminant. The discriminant can be positive if we have real roots which are different. 0 for real equal roots, or negative for complex conjugated pair of roots, where alpha is this part, beta is this with minus, because this is given when D is positive or 0. So we put minus here. And 1 minus square root minus 1, imaginary unit, is placed here in front. So we know alpha, beta. We decide we want underdamped process with oscillations. So there are two conditions. First, the discriminant should be less than 0. Second, we take criteria degree of oscillations to be desired. So alpha over beta gives this expression desired. Then we get rid of the square root in the numerator by putting to power 2 both numerator and denominator, and md to power 2. And the result is that from this expression we obtain Ti as function of Kp. So we give values for Kp and the corresponding Ti is computed. For this couple, if this is first requirement for the discriminant is valid, then this can be a solution. But there are many such pairs. Which one to select? In order to select, we use a second criteria. For each Kp, we compute Ti, and we compute in the frequency domain this integral. For the other pair, new value for I1, and so on, till for some combination, this is the smallest value. We use here as an additional requirement integral squared error minimization, but the maximal rejection of disturbance is ensured when all these ratios of the couples the ratios are compared and the maximum taken. So the tuning parameters should ensure maximum to this ratio. Or reduce sensitivity to plant model uncertainty, because the plant model is after some time will not be corresponding to the real plant because of aging in the very process, in the very installation, and some tolerances. If you know that after 6 months the model will change from this to another one. So this is what we know. We know the possible uncertainty in the model, and we can reduce the sensitivity of our system with respect to changes in the plant model and parameters. This sensitivity function is the integral of square sensitivity. The sensitivity, you know, can be also translated in the frequency domain, considering this transfer function instead of transfer function with respect to error, where S is substituted by j omega. So we can minimize use changing parameters Kp, Ti, Td in the range that they remain positive. So I will give you a graph. It's not here. Okay, maybe in further example. So what remains how we tune higher order systems. So higher order systems can be obtained based on time delay. The time delay ensures infinite degree of the closed loop system, which means the Nyquist plot of the open loop system rotates passing through all quadrants infinite number of times. So it rotates around a small circle around the origin infinite number of times. This shows that the system has time delay. Time delay is a model. In reality, the system is a very high order, but to represent a higher order, we use a simple Ziegler-Nichols model. Time lag, which is first order, and time delay, which compensates the high order. So the time delay is expressed by Euler's formula exactly in the frequency domain. It is cosine omega, so I don't see tau here, cosine omega tau plus j, the imaginary unit, multiplied by sine omega tau. So that's why systems with time delay are precisely designed in a frequency domain because of this Euler's formula. And the method used here, two methods I will show you, which are related with the high order or the presence of time delay. The first method is called expanded magnitude phase frequency characteristics. The expenditure means that S is not substituted by j omega, but by minus degree of oscillation omega plus j omega. So there is a real complex number with non-zero real part. And the real part contains m. M was alpha over beta, and I told you beta is a frequency. So if we cancel beta with this omega, here we'll have minus alpha. So the open loop Nyquist plot is expanded with this m omega. The transfer function uses substitution of S with this complex number. That's why the controller and the plant frequency characteristics depend on the desired value of M for which we want to tune our closed loop system. But this is the open loop from which we can obtain the Nyquist plot. When the Nyquist plot crosses this Nyquist point, we are ensuring the critical stability. So this means that this complex criteria should be satisfied. It could be divided into two real real criteria, one relating the magnitude, the product of the magnitudes of controller and a plant related with the expanded frequency characteristic should be 1, and the sum, this product means the sum of the phases, so we have one phase multiplied by e to something, so the final phase is a sum of two phases of controller and plant, should be -1. Why? Let's return to Nyquist plot. The expanded is similar, differs actually, but to show you the Nyquist plot. Yes. So imagine somewhat modified Nyquist plot, and this is the Nyquist point at distance 1 to the left, so real part -1, imaginary part 0, Nyquist point. So the open loop system is this product, but the open loop expanded characteristic, S will be substituted by -m omega plus j omega. So it will be different, but If this Nyquist plot, so open loop expanded frequency characteristic, reaches Nyquist point, so the critical stability is obtained, and from this condition, how to make this reach this point, we obtain these parameters of our controller. So there are two conditions which are related with the parameters. One, the magnitudes. This makes one equation equal to the product of magnitudes of control and plant would be 1. The sum of the phases minus p because it starts from quadrant 4, from positive axis downwards to 3, that is rotating, so minus p is what takes from plus minus imaginary axis, starting from the plus imaginary axis where we count the phase, the angle, till reaching the Nyquist point on the negative real axis. The angle is minus p. So we have parameters omega unknown here, q, for instance for pi, we have parameters kp and tu. This is the vector q. So we have 3 parameters, 2 equations, because we do not know the frequency. We know m, but q contains all tuning parameters. For pi controller there are 2, and the frequency which is unknown 3. Another equation is necessary. What is done? The ratio kpti is obtained from the first criteria as function of frequency and desired degree of oscillations. This is the criteria for tuning. Kp is obtained from the second, for instance, equation, the phase equation, and it's again function of frequency. So we give one and the same frequency, compute this, and use this coordinate system, Kp abscissa, Kp over Ti ordinate, and the result will be a curve that corresponds to desired degree of oscillations equal to the specified value, connected respectively with time domain overshoot, for instance. And if we take the maximum of this, it is directly maximal rejection of disturbances. If we compute for each point the frequency integral squared error in the frequency domain, like here we have in the frequency domain, the integral square error is minimized for this point. The sensitivity even lower. It requires high gain and small ratio kpti. So additional criteria makes the third equation to select the unique tuning parameters, values of the tuning parameters. High order systems are systems that contain models, plant models with time delay, may use also desired gain and phase margin. We mark the desired gain, so we have to reach this point, and the unit circle crosses the desired angle here, so we have to expand either vector A to reach this point, the desired gain margin, or to expand this vector, this magnitude of the Nyquist plot of the open loop system to reach point 2. So either point 1 or point 2 should be satisfied, and we should have a greater margin with the second indicator. If we ensure exactly the desired gain margin, the phase margin may not be reached but should be greater than desired. So there are several simple rules, program which can easily be constructed to help you. First, you use KP1 and initial value for TI. Obtain the Nyquist plot because it is plant multiplied by controller frequency responses. So you compute for the frequency range important. It is usually related, the frequency range is determined by the time constant of the time lag model of the plant. The time constant, 1 over the time constant is the basic frequency. We have one order smaller and one order higher frequency. So the frequency range is known. You draw this Nyquist plot and you can measure A multiplied by different than 1 gain should result in this point. This point is magnitude 1 minus the margin, So this magnitude, A to point, from origin to point 1, should be reached by using this gain. So we compute the gain. The same is done with the other margin, the phase margin. This should be multiplied by gain, another gain. So the magnitude B is multiplied by gain to reach final magnitude equal to 1, because this is the unit circle. So this is 1. The radius is 1. So we compute the two possible gains and take the minimum of them. So we'll ensure fixed margin on phase, for instance, and greater margin on gain, or vice versa. So then we start with KP1, and so for TI1 we have already obtained KP1, but now we change TI2, KP is again 1, and repeat the procedure. We obtain several couples KP corresponding TI. KP that corresponds to Nyquist plot with the given TI. And the selection between these several couples KPTI, you select this couple that ensures maximal disturbance reduction, maximum of this ratio. So here you may reach underdamped process because M previous criteria means that desired M is reached only at dominating complex conjugated pair. So oscillations are expected, while C and gamma, they locate the root at some distance to imaginary axis in the root plane, and this is the margin. It could be complex conjugated pair roots, the real part, or real root located at that position. So we can have both stability margin and gain and phase margins defined for underdamped or overdamped, even for critical transient response, step response. So experimental methods. Experimental methods, Ziegler-Nichols is the most widely used, but it ensures some overshoot 25%. So oscillations. Many experiments are performed with increasing gain or decreasing gain. The idea is that you take a small gain, you have a great steady state error, and some oscillations or overdamped process. You increase the gain till the oscillations increase in magnitude and become sustained. Further increase, you lose stability. But you see the oscillations are around the settled value, but they will never settle these oscillations. But the steady state error decreases. Of course, this dashed line, the settled value line, reaches closer to reference. We are interested in reaching sustained oscillations with equal magnitude. We measure the time between two peaks. This is the period of oscillations. And we measure twice the magnitude, the difference between maximum and minimum. So this gives twice the magnitude of oscillations. These measurements allow us to recompute the parameters. Here we have only proportional controller and change the gain for measuring finally Ku, for which we have sustained oscillations with given period and given magnitude you can measure. So this is the ultimate period, the period of the sustained oscillations, and this is reached for gain Ku. So the theory is that Ku is 1 over the closed loop magnitude for the P frequency. This is the frequency where the phase is minus P. So we are crossing the Nyquist point, this minus P. T ultimate is also related with omega P. So this is the critical stability. So we are in the point, Nyquist point, if we consider the Nyquist plot of the open loop system. So knowing Ku and Tu, we compute for different controllers the parameters function of Ku, Tu. For instance, for proportional controller, we have 0.5 of Ku. This is the tuning parameter that ensures the desired performance indicator, 25% overshoot. Kp is present at PI controller and PID controller. It is reduced at PI because I influences decreases stability margins. Here we can increase because the D component neutralizes the I component and helps increasing the stability margin. So here Ki or Ti, so Ki and Ti are related. So we have for Ki this formula, for PI controller. This is the coefficient in front of the integrator, and the coefficient in front of differentiator. So this is the differentiating coefficient present only in the PID controller. There are such tables for other simulation experiments. But to finish with this one, there are advantages because during the experiments you don't need a model of your plant. All deficiency of the plant related with nonlinearity, change of parameters, disturbances, they are included in the step response which is used in the obtained in the experiments. But we need many step responses. So first for this. Then second, third, so 10 till you reach this one. And it takes a lot of time. And it is also, you reach steady state, you have to return to initial steady state. Again, 2 times settling time. You have to reach settling here and then returning back. So it is a quiet time, and it influences the process. So you do not every system allows experiments which may interfere the quality of the production produced. Disadvantages also. We need smooth change, so many changes of Kp till we reach Ku. Some disturbance may introduce false sustained oscillations. In fact, we have no control on the environment. It's not very precise, and the tuning is related with oscillating step responses of the tuned closed loop system. But you know, overshoot means the temperature goes about reference, so burning of the bread in my previous example. Then this is the table, empirical or engineering, using experience and simulation tuning methods, different methods. They all accept Ziegler-Nichols plant model. We'll use various overshoot formulae in which A, B, and C gains differ for different controllers, proportional, PI, and PID. So A, B, C, that ensures sigma 0, because here the others do not ensure underdamped process. They all have some overshoot. 25% without experiment Ziegler-Nichols. Minimum integral square error, which ensures oscillations and requires high control action. You say decay ratio, which means there is a second maximum, Y3. So first maximum, second maximum, so the oscillations are significant. But here we have sigma 0, sigma 25, sigma 45, which corresponds to integral squared error about minimum. And A, B, and C take values for the different controllers. You use these formulas. Kp depends on K and relative delay, tau over T. Then T goes in numerator. So relative delay and the gain, their increase may cause instability. That's why for high gain and relative delay, we have smaller gain of the controller. The higher gain of the controller will make the system unstable. So why? Because the gain expands Nyquist plot and may reach Nyquist point, while the time delay over the time constant, when increased, rotates the Nyquist plot so that the higher magnitudes will approach the Nyquist point, the critical stability point. So we take values for the gain. A is related with the gain of the controller. It's smaller for proportional, great increased with the PI, and the biggest for PID. So this ensures zero overshoot. For greater Kp for the corresponding controller, everywhere for each controller this value is greater, then oscillations appear with small overshoot. Still increasing the gain in a column for a given controller results in increasing oscillations and the overshoot. Overshoot, the dynamic deviation above new reference is increased for the same step change of reference. So, about tuning of digital controller, which will be our last topic for today. Digital controllers, all are digital controllers. The PID control action is described as a function of error in current moment and moment, one pass moment and two pass moments. So the previous moment and the moment before the previous with different coefficients, and this is the previous control action. This PID control algorithm is called position. We know exactly the control action. We update the previous controller with this part, which can be called delta U. Delta U is this part. So, if we use delta U, this is the difference between current control action and previous time control action. So, this difference is proportional to derivative, or that's why this is called incremental speed PID controller algorithm. So when we obtain or use this speed control algorithm, it is assumed that this derivative of control action needs integration, because this is the output which controls actuator of the valve actuator couple. Actuator can be a motor, and if this motor is a dynamically integrating element, we use the actuator to do this integrating of delta U. Else, delta U is added to previous to obtain the position control action. So, previous plus delta U. So, we compute delta U in the algorithm, memorize in a cell of the memory of the digital controller previous control action, and update this with delta U to obtain the current control action. In digital controllers, we have measuring of controlled variable in discrete moments and application of the control action in discrete moments. So the discretization is with equal time step size delta t. As these A, B, and C depend on the analog controller, parameters Kp, Ti, Td. In the analog controller, the integrator is substituted by sum of discrete measurements. When we have measurement, reference minus measurement gives us the discrete error. So we have PID proportional integral. I told you it's a sum, and the differentiating is finite difference. For error, this is error at moment n minus error at moment n minus 1. This will be the derivative of error. We substitute this in the analog algorithm and obtain this discrete algorithm. Kp, Ti, Td are Turing parameters of the analog controller, and they can be preserved using one of the previous methods for tuning, but we add delta t. Delta t is another Turing parameter, and it should be considering the cutting frequency. So we have to select this according to this formula, or the natural frequency, which is close to the peak frequency, or there are specific formula for computation of the sample period. Probably these formulas, we have formulas, empirical tuning methods for digital controllers, and they contain not only the model parameters, but also delta t and the analog controllers parameters like Kp, Kp, Kp. So the result is the digital controller has the same stability margins like the analog when we properly select the sample period. I forgot to tell you this combination of tau and t in a formula. Usually delta t is 0.1 tau or t, depending which is bigger. So you see a lot of empirical methods from experience obtained how to make the digital control system equivalent in sense of stability margin to the analog control system, where the digital component is the controller, the plant is analog. So we apply the methods, select correctly delta t, and obtain step responses similar like the step responses of system with analog controller. Today, we do not see much of the analog controllers. Most are digital, and the sample period is no problem. It could be made very, very small because the new programmable logic controllers work with very high frequency. So, up to here, we have done a lot of the material. From next time, we would have a short lecture, not 5 periods using the time for break, but we won't have break, but wouldn't need to stay late. We'll finish earlier. But till next week, I need your MATLAB installation on your laptops or computers. So I spoke about tutorials using MATLAB. You can see how you can download MATLAB from internet and install it. One of your colleagues mentioned he has installed MATLAB 2018. Is the boy here now? Last year, MATLAB 2020 was installed from torrents. It's illegal. There is a breaking of the key. And we could manage with tutorials. You have 3 tutorials. And next time, after the short lecture of 2 periods, I will have a tutorial to introduce you how MATLAB works. And during the lecture, we'll speak about Smith predictor. So you have to prepare this manual. It's no need to read this, but we'll discuss how to use this because the lecture before will contain the theory related with this tutorial. So it's lecture 3, compensation of plant time delay And this is the Smith predictor, you see. I'll give you the lecture and we'll continue with the first tutorial using MATLAB. So this week you have to install, and if you have problems, you have to write me to my email or use the mobile. Have you written my mobile? I'll write it
Yes,
again.
I yes I read it.
Okay, I will stop recording.